Thank you very much. My name is Tetsuaki Moriguchi from University of Tsukuba. First of all, I'd like to thank the organizers and Professor Iwata to give me the chance to talk here. So my title of presentation is Advantage of Spin-Polarized Fusion. So this type of fusion is so very minor fusion compared to the thermonuclear fusion. So first, let me introduce myself. My study field is experimental nuclear physics using several accelerators, using tandem accelerator at the University of Tsukuba, RIKEN RIBF, QST, HIMAC. So my interests are nuclear radii, nuclear mass, and nuclear moment. So in the study of nuclear moments, I used polarized ion source at the University of Tsukuba. So recently, I've been interested in the spin-polarized fusion as a way of using this polarized ion source. So actually, the study of my spin-polarized fusion is not started yet. But in this presentation, I will show you what spin-polarized fusion is and its advantage. So this is the outline. First, I'll show you the fundamentals of nuclear physics towards fusion reactions. So a part of my slide is similar to the previous talker, Okara-san. So Okara-san give me a very nice introduction of fusion. So these are the keywords. So in the second half of, I will show you the spin-polarized fusion and its advantage for polarized deuterium-tritium fusion and polarized deuterium-deuterium fusion. And finally, I'll summarize my talk. First is this one. So as you know, the material consists atoms, and atomic nuclei is surrounded by the electrons. So nucleus consists of protons and neutrons. It's called nucleon. So this is periodic tables. Presently, the 180 elements are listed here. And in hydrogen, hydrogen has three isotopes like this: proton, neutron, and tritium. So this is a nuclear chart. So the vertical axis means a proton number, and the horizontal axis is a neutron number. So one square corresponds to the one nucleus. So the number of projected nuclear species around 10,000, but this number depends on the nuclear theoretical model. And actually, the number of discovered nuclear species around 3,000. So the many of nuclei is not observed yet presently. So the atomic nuclei can be divided to stable nuclei and unstable nuclei. So stable nuclei can exist naturally, and the number of stable nuclei is around 300. And the unstable nuclei decay to the stable nuclei with the finite lifetime. The number of unstable nuclei are all nuclei except for stable nuclei. So the white region indicates the unknown, unobserved nuclei. So to form a nucleus, the binding energy is needed. So binding energy can be expressed by this equation based on the energy mass equivalent law. So the mass of nucleus is lighter than the sum of free nucleons like this. So the difference corresponds to the binding energy. So this graph shows a binding energy per nucleon as function of mass number. So for nucleus with large binding energy, it means it's hard to remove nucleon from nucleus. It means that the nucleus is stable. So as shown here, the iron or nickel, the binding energy of iron or nickel is stable, high. Binding energy is high. So this nucleus is very stable. So I will show you the nuclear reaction briefly. So nuclear reaction is disturbed by a Coulomb barrier. So Coulomb barrier can be expressed this equation. And this graph shows the potentials of Coulomb, this one, and the nucleus, this one, and the sum of nuclear and Coulomb, this solid line. And this height corresponds to the Coulomb barrier. So this is a schematic view of the potential. So when the incident energy is lower than Coulomb barrier, the incident particles can enter into the target nucleus. But so incident energy is larger than Coulomb barrier. The incident particles can enter inside the target nucleus. So nuclear reaction can be occurred. So for example, is a fusion. One of nuclear reaction is fusion, like this. So this these values are Coulomb, height of Coulomb barrier of these fusion reaction. So in nuclear reaction, we should understood in quantum mechanics. So according to quantum mechanics, even though energy is lower than Coulomb barrier, the incident particle penetrate to the Coulomb barrier. So incident particle into the target nucleus. So fusion reaction for this quantum tunneling is important for fusion reaction. So there are some many types of nuclear reaction, elastic scattering, inelastic scattering, and transfer, stripping, fusion reactions, and so on. So in this one, in this case, the nucleus is changed after the reaction. So for nuclear reaction, energy is very important. So this is a schematic view of energy level of this nuclear reaction. So this is a compound nucleus in intermediate state between initial and final state. So this is a Q value. Q value is incident energy. When incident energy is larger than Q value, this reaction is occurred. And if if this compound nucleus have excited state here, when incident energy is correspond to the energy of this level, the reaction is enhanced. The cross section of reaction is enhanced. This is resonant reaction. This resonant reaction is also important for fusion reaction. So I will show you the fusion reaction for nucleosynthesis in the star. So for a nuclear physicist, fusion reaction is familiar with nuclear synthesis. So in the early stage of star, hydrogen burning produced helium through these proton-proton chain and CNO cycle. And then helium burning started. and then carbon burning started. So this nuclear burning continues to up to iron and nickel region because the binding energy of this element is high, so very stable. So this is the example of evolutionary stage of stars. And the energy in the sun is produced by proton-proton chain in hydrogen burning like this. So for fusion, I will show the fusion reaction for energy production in the Earth. For fusion, for energy production, these DT fusion or DT fusion, D-helium-3 fusion are proposed presently. So this graph shows cross-section. Cross-section means reaction probability. So cross-section as function of the energy of relative motion. So here and here is the cross-section of deuterium, tritium, and deuterium helium-3 is larger than deuterium. So this is energy level of triton and fusion. So the helium 5 in intermediate state have resonance state here. So this enhancement of the cross section corresponds to the resonance reaction here, and it's similar to the helium-3 deuteron. So the lithium-5 in intermediate state have a resonant state here. So this enhancement is due to the resonant reaction here. So I will show you the spin-polarized fusion and its advantages. So before the spin-polarized fusion, I will show you the nuclear spin. So in classical mechanics, nuclear spin is rotation of nucleus. And as you know, the nucleus have positive charge. So the rotation of positive charge means electric current. So electric current produces a magnetic field from Biot-Savart law. So in quantum mechanics, the magnetic quantum number of spin allows this value, and the number of magnetic quantum number is totally 2I plus 1. And this is the spin of these nuclei related to the fusion. So I will show you the spin coupling. So assuming this reaction, the coupled spin allow these values. So that when the spin directions of A and B is same direction, it's called parallel. So parallel. So the coupled spin is maximum like this. On the other hand, when the spin directions of A and B is opposite, it's called anti-parallel. The coupled spin is minimum like this. So this coupling spin is important for spin-polarized fusion. So I will show you the spin-polarized fusion. It's called SPF. So the idea of this was proposed more than 40 years ago in this literature. So in the case of polarized fusion, the spin directions are aligned along the quantum quantitation axis. This case is parallel, and this case is anti-parallel. So in the case of unpolarized fusion, the spin direction is not aligned along the quantitation axis. So I listed the advantages of spin-polarized fusion. One is increase of the reaction rate. For DT fusion, the cross-section of polarized fusion is 1.5 times larger than the cross-section of unpolarized fusion. So it means an increase of energy production. And the second is anisotropy of angular distribution of reaction products. So from this, we can control the emission direction of these reaction products. And the third is the reduction of neutron-producing reactions. So it means a reduction of the radioactivation of the reactor. So from now, I will show you the detail of these advantages. So first, I'll show you the applied DT fusion. So the spin of deuterium is 1, and tritium or helium, the spin of tritium or helium-3 is 1/2. So coupled spin allows 3/2 or 1/2. So in the case of in the parallel case, the coupled spin is 3/2. The spin of helium-5 in intermediate energy, intermediate state, is 3/2. So this coupled spin is equal to this one. So this reaction is allowed. And in the case of anti-parallel case, the coupled spin is 1/2. This value is not consistent with the spin of helium-5. So this reaction is not allowed, forbidden. So this is a cross section on unpolarized fusion. So the cross section of unpolarized fusion can be expressed by this equation, and this term is equal to 0 because the anti-parallel case is forbidden. So this is a cross-section of polarized fusion. In the case of polarized fusion, the contribution only this parallel case. So consequently, the polarized cross-section of polarized fusion is 1.5 times larger than the unpolarized case. So this is a very big advantage of spin-polarized fusion. So, and I will show the angular distribution of reaction products for DT fusion. Differential cross-section can be explained this equation using differential cross-section for unpolarized fusion and angular distribution function W. So using this expression, the angular differential cross-section of unpolarized fusion parallel case, anti-parallel case is like this. And this is angular distribution as function of polar angle. So these curves correspond to this function. So from this, so it's possible to control the emission direction of reaction products. So from point of view of the reactor, the neutrons could be diverted from the wall of the reactor, and helium-4 could be directed into the plasma for enhancing the plasma temperature. This very benefit for all the fusion reaction in the reactor. Presently, the studies of developments for measurement of the polarization lifetime of polarized deuterium helium-3 fusion is ongoing at D3D Tokamak in the USA. This is this may be a recent report, and this is a result of simulation of lifetime polarization lifetimes for spin parallel case and anti-parallel case. But so it seems that there is no experimental data, but maybe a measurement of the polarization or lifetime are upcoming. So I will show you the price due to DD fusion. So the spin of deuteron is 1. So the coupled spin around 2, 1, 0. So for the anti-parallel case, the coupled spin is 0. The spin of helium-4 in intermediate state is 0. So this coupled spin is equal to that of helium-4. This reaction is allowed. But in parallel case, the coupled spin is 2. This value is not consistent with the spin of helium-4. So this reaction is not allowed, forbidden. So neutrons are produced via DD fusion during the DT or D helium-3 fusion. So using the polarized DD fusion, the production of neutron is suppressed. So this is my image of polarized fuel in the reactor. So in the parallel case, so for spin polarized fusion, the cross section of DT fusion is enhanced, and the DD fusion in the DD fusion, no neutron is produced. Actually, the DD fusion involves P and D wave reaction together with S wave 1. So the expression of DD fusion reaction is very complicated. So this is a quintet suppression factor called QSF. QSF can define the ratio of a cross-section of parallel polarized fusion and the unpolarization cross-section of the unpolarized fusion. So when the QSF is less than a unit, the production of neutron is suppressed. So this is a QSF as function of the energy. So there are many data, but these data is only theoretical calculations. There are many calculations. They are here. So QSF depends on the theoretical calculation as shown in this graph. So there are no experimental data in this graph. So up to now, no experimental data is reported yet. So experimental data is desirable. So finally, I'll show you the present progress. So studies and developments for measurements of double polarized DD fusion is ongoing in Russia, Germany, Italy, and Greece. So there are two experimental collaborations exist. One is a polyfusion collaboration. So in the polyfusion collaboration, this system is used. So polarized atom beam and ion beam is collided at here. So the reaction at the reaction point, there is a 4-pi detector. So other one project is prefer collaboration. So in this literature, the overview of this project, this collaboration is mentioned. But so this study and development is ongoing, but presently there are no experimental data. So measurement of double polarized DD fusion is upcoming. Okay. In summary, fusion reactions, DT, DD, D helium-3 are important for the energy production in the Earth. In low energy, the quantum tunneling effect is important for fusion reactions. For DT and D-helium-3 fusions, cross-sections are enhanced due to the resonant reaction. So the advantage of spin-polarized fusion, one is the increase of the energy production and control of the emission direction of reaction products and reduction of neutron producing reactions. So presently, experimental data for spin-polarized fusion is very poor. So and studies and developments for spin-polarized fusion are ongoing. So that's all. Thank you very much.